Hey guys, it's me again. We're going to do another little bit on sequences and series, and this time it's called recurrence relations, and this is a really popular exam topic. So most of my teaching on this is actually going to be from some of the new spec exam questions. So a recurrence relation should remind us of some of the things that we've done with like iteration. It's kind of like an iterative formula in some ways. So this one here that I've got as an example, this is not a recurrence relation. It says this is an example of a position to term sequence because each term is based on the position n. So if I wanted to find out what the 50th one is, all I need to do is substitute 50 in. However, a term might be defined based on the previous terms. So here I have u of n plus 1 equals 2un plus 4. If un refers to the current term, un plus 1 refers to the next term. So the example in words says the next term is twice the previous term plus 4. Okay? So to find out what the next term is, you look at the previous one, you double it, and then you add 4. And these are actually really good ways of being able to represent things because they often don't have formulae that look like this, okay? They have to just be defined in terms of what happened beforehand. So I've said here that u1 is equal to 3, because if you don't know what the first thing is, you're not going to be able to find out what the next one is. So I've said here we need the first term because the recurrence relation alone is not enough to know what number the sequence starts at. So I'm saying it's going to start at 3. That's what the first term is. The next one, though, is you take 3, you double it, which is 6, and you add on 4, which is 10. And then to find the next one after this, you double it, which is 20, and you add on 4, which is 24. And then you double it again, which is 48, and you add on 4, which is 52. And you'll very clearly see that this is neither geometric nor arithmetic, because it's going up 7, 14, it's going up in a kind of a different kind of pattern that we've got here, and it's also not a multiplicative pattern, so it's a recurrence relation instead. So this is known as a term-to-term sequence because you're going from one term to the next, or more formally as a recurrence relation, as the sequence recursively refers to itself. Important note, with recurrence relation questions, the sequence will likely not be arithmetic nor geometric, so your previous UN and SN formulae do not apply. So these questions are kind of separate, and you just need to explore them and spot patterns that happen. But I really like these questions. I think they're really interesting. So I'm actually just going to go straight in with doing a whole set of exam questions. If you want to like pause and have a go, you're welcome to. So here we go. This time I've got a sequence that they're using the letter x. x1, x2, x3 is defined by the first one, x1 is 1. And then to find the next one, you take the previous one and square it, and you subtract k multiplied by the previous one. And it says that n has got to be greater than or equal to 1 because it's just referring to these integers that we have here. So find an expression for x2 in terms of k. Well, if you're trying to say what x2 is clearly going to be equal to x1 squared minus kx1. But we know that x1 is 1, so it's just going to be 1 squared, which is 1 minus k. Show that x3 is equal to this. Okay, well, x3, we know, is x2, the previous one, squared, x2 squared minus k lots of x2. But x2 is 1 minus k. So I'm going to substitute 1 minus k and square it, and I'm going to do k lots of 1 minus k. So when I expand this, I get 1 minus 2k plus k squared minus k. Careful of this last bit, it's a negative and a negative, so you get a plus k squared. So you end up with 1 minus 3k plus 2k squared, exactly as they wanted it to be here. Given also that x3 is equal to 1, calculate the value of k. So I now know that this thing is 1. So I get 1 equals 1 minus 3k plus 2k squared. So I get, subtracting 1 from both sides, I get 0 equals, and just flipping these around, 2k squared minus 3k. I'm going to just factorize out a single k. So that's k, which is 2k minus 3. So here what am I going to do? Solve this, so I either get that k is equal to 0 or k is equal to 3 over 2. And that's perfectly fine. K could be equal to 0 if x3 is equal to 1. It's just not going to be a very interesting kind of sequence that we get here, because each of them is just going to be 1, and then it's going to be 1 minus 0, so it'll just be 1, 1, 1. Each number in the sequence is just going to be 1. So I want to see what they've actually put in the mark scheme for that one. They've said that k has got to be 3 over 2. I wonder why. I think that k could be 0 as well. Is there anything that says that? K is a constant. I think k could be 0. But anyway, we're going to run with this one instead, that k is 3 over 2. So hence find the value of this thing that we've got here. Okay, well, if k is 3 over 2, we now know we're just going to have to substitute in some values and see if there's a pattern, because the previous rules do not apply. So x1 is 1, we already know that. x2 is 1 minus k, which is 1 minus 3 over 2, so that's minus a half. And then we know that x3 is going to be equal to 1. Well, when you put 1 in, you get minus a half as the next one. So the sequence that we've got, or sorry, the series goes 1 plus minus a half, plus 1 plus, well, when you substitute 1 into this formula, you get minus a half. So it's going to be a series that just keeps going on and on and on and on, like this. And there's going to be 100 of these terms. Now, if there's 100 of these terms, that must mean that there are going to be 50 of these repeating pairs that we have got here. There's going to be 50 of these repeating pairs for the sum from n equals 1 to 100 of xn. Now, 1 minus a half is just going to be a half, and there are 50 of those pairs, so it all adds up to 50 over 2. Now, you can't type this into your calculator, okay? This one is not possible to type into the calculator, so it all adds up to 50 over 2. Oh, what am I? 50 over 2, I didn't even put that as an integer. So it adds up to 25, which you can see is what we do have over here. See all these pairs of it coming up like that. Okay, we're just going to keep going. We're going to keep doing more examples on this one. So for 3a, it says a sequence of numbers a1, a2, a3, where a1 is equal to 3. And to find the next one, you do the previous one take away 3, divided by the previous one take away 2. So let's just try and find out what this looks like. So for the first one, a1 is equal to 3. Now a2 is going to be equal to 3 minus 3 over 3 minus 2. So that's 0 over 1, which is just 0. Interesting. So now let's try and find out what a3 is. So we're going to use the previous one, take away 3, over the previous one, take away 2. Well, the previous one is 0. So it's going to be 0, take away 3, over 0, take away 2, which is just minus 3 over minus 2, or 3 over 2. Okay, let's try and find out the next one is. It's going to be 3 over 2, take away 3, over 3 over 2, whoa. Three over 2, take away 2. Well, 3 over 2, take away 3. I'm just going to put this all in a calculator. I'll tell you what, I'm just going to be lazy. 1.5 minus 3 divided by 1.5 minus 2. And we end up with 3. Now, if we wanted to find out what a5 is, we would be putting 3 into this thing again. But we've already done that. And when you put 3 in, we know that you get 0. And predict what a6 would be. When you put 0 in, oh, we've already done that. You get 3 over 2. So it looks like this series from r equals 1 to 100 of AR, you notice we've done a lot of substitution. This is where loads of the marks are going to be. It's just going to be equal to 3 plus 0 plus 3 over 2 plus 3 plus 0 plus 3 over 2 plus, and that's going to keep going, okay? Now this time we get them repeating in groups of 3, okay? So how many groups of 3 are we going to have? Well, it's going all the way up to 100. So 100 divided by 3 is 33 and a third. So there's going to be 33 groups of 3 plus 0 plus 3 over 2, because there's 100 things here. 1, 2, 3, 4, 5, 6, all the way up to 100. And we need to know that there's going to be 33 of these complete sets of 3, 0, 3 over 2, 3, 0, 3 over 2, 3, 0, 3 over 2. And so there's going to be one extra number that comes at the end that's not going to be a complete set. Well, it goes 3, 0, 3 over 2. There's going to be 99 of those. And so the last one will be the start of this one, which is an extra 3 that we have here. So that's 3 plus 0 plus 3 over 2, multiplied by 33 plus 3, and we get 151.5 for that first bit. And then it says, find the sum of this first thing that we've got here, plus the sum of it all the way up to 99. Well, we know that up to 99 was all of this bit. This was the 100th one. So if I want to, for part B of the question, if I want to do from r equals 1 to 100 of AR, plus the sum from r equals 1 to 99 of AR, well, it's 151.5, because we've just worked that bit out, plus 33 lots of the 3 plus 0 plus 3 over 2, but I'm not going to bother writing the 0 this time. So I'm just going to add those together. So that's 3 plus 3 over 2 multiplied by 33 plus 151.5, and we get the answer 300. Okay, let's see if we got that right. 151.5 and 300. Did they seem to do it in a different way? No, they've just got the same as us, 33 of those groups of 4.5, which is the 3 plus 0 plus 3 over 2, and then the 100th one was the 3 that they've got added on there as well. They did it in a slightly different way. They did 2 lots of this one, and then they took away a 3, but I'm happy with the way that we did it, of just doing all the way up to 99 and adding on an extra one of those. How many more have I got to do? I'm going to do a few more. I think the more you can see, the better, while I'm not actually able to teach you fully. So here we go, we've got another one. This time you've got this sequence, okay? So it's to find the next one, you do k minus 3k over the previous one, where k is a constant. The sequence is periodic of order 3. Now this something, I don't know if we've actually come across periodic. Did we talk about periodic before? Let me see if we did. If we didn't, I might mention it now. No, we haven't done, but I can quickly mention it now. A sequence is periodic if the terms repeat in a cycle. The order k of a sequence is how often it repeats. So this one, which goes 2, 3, 0, 2, 3, 0, 2, 3, 0, is periodic and has order 3. So although I'm doing something that's not quite available to us yet, I will do. So that means it's going to repeat. It's going to be 3, and then it will start looping back around again. So it says, given that A2 equals 2, show that this thing is going to happen. Okay, well, if A2 is equal to 2, let's find out what A3 is equal to. Well, it would be k minus 3k over 2. So that's k minus 3k over 2. So that's 1 minus 3 over 2, which is minus k over 2. So that's what A3 is equal to. And A4 is going to be equal to k minus the previous one, which is 3 multiplied by minus, that's not true at all. Sorry, it is k minus 3k over the previous one, which is minus k over 2. So the k's are going to cancel for that bit that we've got here, as are the negatives. So it's going to come a k plus 3 over 2. So the k's cancelled, and then the negative and the negative cancelled, so it becomes k plus 3 over 2. And I'm going to work out what the next one is, because that's going to help me know that if it's periodic, because it's going to go 1, 2, 3, and then it's going to repeat itself. So it will be k minus 3k over the previous one, which is k plus 3 over 2. Now, because it repeats and it's periodic, that means it's going to go like A, B, C, A, B, C, A, B, C, repeating it every 3 times because of order 3. So that means it's going to go 2, something, something, 2. So this thing here must be equal to 2. So let's actually do some calculations. We now know that 2 is equal to k minus 3k over k plus 3 over 2. I'm going to multiply everything by k plus 3 over 2. So that's 2 k plus 3 over 2 equals k plus 3 over 2 minus 3k. Expanding the brackets, 2k plus 3 equals k squared plus 3 over 2k minus 3k. Looks like I'm getting a quadratic here. So where has something gone wrong? Let's see if I've done a mistake. So we've got 3 over 2k minus 2 minus 3. Why have I got that different to this? Did I substitute these in right? K minus 3 over 2, k minus 3k over 2. It's minus k over 2. Ah, this bit I've done wrong. This bit is not correct. My mistake. Take it a bit slower and I won't make as many mistakes. So it's actually k minus, cancelling the k's out, 3 over minus a half. And 3 divided by minus a half, or minus 3 divided by minus a half, is actually 6. So it's actually k plus 6. So that was my mistake that I made there, which means this should have been k plus 6. It's still going to be equal to 2. It's just this bit here is wrong. That should have been k plus 6. And so here, everything should have been multiplied by 6. Here it is, and here it is. So that's 12 going here. That is 6k. And so let's really hope this works. So it's 6 minus 3 minus 2. Good. So I get k squared plus k minus 12 equals 0. Given that a1 is not equal to a2, find the value of this thing that we've got here. Okay, well, I've been given a quadratic, right? I better solve that quadratic, and I'm going to be, as you can see, super lazy today. I'm going to go back to my polynomial. I don't know why I'm not factorising this. You'd have told me off if we were in class. So either k is equal to 3 or k is equal to minus 4. Well, we better find out what's actually happened here. We know that a1 is not equal to a2, so it's got to be periodic. Let's actually see what happens if we were to substitute in these different values. So we've got that a2. Let's pretend that k is equal to 3. So if k is equal to 3, we get that a2 is 2, a3 is minus k over 2, so that's minus 3 over 2. a4 would be equal to 6 plus 3, which is 9. And a5 would be equal to... what am I looking for? This one. Oh, a5 is equal to 2 as well. We already know that. What about if k was equal to minus 4? We would get that a2 was equal to 2, a3 was equal to minus 4 over 2. So it's minus 4 over 2. Well, that's just going to be 2. a4 would then be equal to 6 minus 4, which is 2. And a5 is equal to 2. So this is a pretty boring sequence where every number is 2, 2, 2, 2, which means that a1 would be equal to 2. So this means that k cannot be equal to minus 4 because a1 would have been equal to a2 if k was equal to minus 4. That must mean that k is equal to 3. So although that felt like a lot of work, we actually still we've not overdone it. So we now know that the series is going to go 2 minus 3 over 2 plus 9 plus 2 minus 3 over 2 plus 9. But remember, this is A2, A3, A4, A5, A6, A7. So the one that comes before the 2, because we need to start off with A1, is 9. So it actually goes 9, 2, minus 3 over 2. 9, 2, minus 3 over 2. So our sum from r equals 1 to 121 of AR is equal to this that we've got here. Now 121, when you divide it by 3, is 40 and a third. So that means that there are going to be 40 lots of these little triplets. I should have put some dots here. And because there's 40 and a third, we know that there'll be 120, that all of these groups come up to 120. The last one will be the start of this, so there'll be an extra 9 at the end. So there's going to be 40 lots of 9 plus 2 minus 3 over 2, and then there's going to be an extra 9 added on at the end. That's because this 40 multiplied by these things represents the first 120, and then this is the 121st one. Remember, we had to go back to find out what A1 was, and we did that knowing that it was a repeating kind of pattern. So that's 9 plus 2 minus 3 over 2, multiplied by 40, plus 9, and you get the answer 389. Okay? Let's see if that is correct. It is. Great. So we rejected this one as well. Looks like we've done everything that's correct in this bit. I am going to take a pause here because I feel like we've done a lot, and then I will just do this exam question and this exam question, and then you can probably already do exercise 3G, but I'm just going to split the video up.